Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent spaces between worlds, where shadows drift and secrets wait in the darkness near Mars. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the vast quiet of space, telescopes sweep the darkness with patient electronic eyes. The 3-Eye Atlas survey system moves its gaze across familiar territories of rock and ice, cataloging the predictable dance of known objects. Night after night, the same asteroids trace their ancient paths through the solar system's asteroid belt. The same distant stars hold their positions like cosmic lighthouses, their light traveling millions of years to reach Earth's instruments. Everything follows the mathematics of gravity and time, as it has for billions of years since the solar system settled into its current configuration. The survey operates with mechanical precision, photographing the same patches of sky repeatedly, comparing images to detect anything that moves against the stellar background. Most discoveries reveal themselves as bright dots that shift position between frames, new asteroids reflecting sunlight, comets developing their characteristic tails as they approach the sun's warmth, or distant galaxies whose light has traveled across cosmic time to reach our small corner of space. The process continues with the patience of geological time, accumulating data about the solar system's inventory of wandering objects. Then, something different appears in the data streams flowing back to Earth through radio telescopes and fiber optic cables. Not the bright flash of a new comet catching sunlight on freshly sublimating ice, not the steady glow of reflected starlight from tumbling stone. Instead, the instruments detect something that seems to drink light rather than share it with the cosmos. A patch of darkness that moves against the star field, occluding distant suns as it passes in front of them like a celestial eclipse in miniature. The astronomers reviewing the nightly data downloads pause in their routine analysis, recheck their calibrations with the careful precision of scientists who understand that extraordinary claims require extraordinary evidence. Run the numbers again through multiple verification algorithms. The object appears in frame after frame, consistent in its movement, undeniable in its presence. Only took 4 billion years of solar system evolution to notice something this substantial drifting so close to our planetary neighborhood. The object occupies the space near Mars, following an orbital path that speaks of capture rather than birth within our solar system's familiar gravitational architecture. Its trajectory carries the distinctive mathematical signature of something that wandered in from the interstellar void and found itself caught in the sun's gravitational embrace, like a cosmic wanderer finally finding rest after eons of travel through the galaxy's empty spaces. The orbital mechanics suggest a history written in the language of celestial mechanics, a story of gravitational encounters and gradual capture that may have unfolded over millions of years. How long it has maintained this patient orbit around our sun remains shrouded in uncertainty. Perhaps it arrived when Earth was still a molten ball cooling from its violent formation, when the solar system itself was young and chaotic with planetary migration. Perhaps it slipped into our neighborhood more recently, in the cosmic sense of recent, drawn by the sun's gravity during one of our star's passages through the galaxy's spiral arms. The object carries no obvious signs of its age, no surface features that might speak to its origin story or the eons it has spent in space. What strikes the observers most profoundly is not what the object reveals about itself, but what it so deliberately conceals behind its enigmatic surface. Unlike every other substantial body catalogued in the solar system, this wanderer reflects almost no light at all. It absorbs wavelengths across the electromagnetic spectrum with an efficiency that challenges current understanding of materials science. The darkness it presents to telescopes appears nearly absolute, as if space itself had somehow condensed into solid form and learned to orbit the Sun with the patience of geological time. This light-absorbing behavior defies easy categorization within the known taxonomy of solar system objects. Asteroids, even the darkest carbonaceous varieties, reflect some percentage of incident sunlight. Comets develop bright comas and tails when solar radiation sublimes their surface ices. Even the most distant and cold objects in the outer solar system show up as dim but detectable points of reflected light when powerful telescopes turn their attention to them. This shadow object seems to exist outside these familiar patterns, following its own rules of interaction with electromagnetic radiation. The mystery deepens with each night of additional observations. Initial estimates, derived from careful analysis of how long the object takes to occult background stars, suggest it measures several kilometers across in its longest dimension. Large enough to cast measurable shadows when it passes between Earth's telescopes and distant stellar sources of light. Large enough to represent a substantial mass in the context of solar system debris. Yet, its surface temperature, barely detectable even in the most sensitive infrared observations, registers slightly warmer than the cosmic background radiation and surrounding vacuum should theoretically allow. This thermal signature hints at internal processes that current models struggle to explain. Perhaps radioactive decay of long-lived isotopes buried within the object's core continues to generate heat after billions of years. Perhaps some exotic material property allows it to trap and slowly release solar energy in ways that conventional materials cannot. Perhaps the darkness itself serves some unknown function in the object's thermal regulation, like a planetary-scale version of technologies that remain beyond human understanding. Scientists studying the accumulating data find themselves confronting questions that have no ready answers within the current framework of planetary science. The object's composition remains completely unknown, hidden behind its light-absorbing surface like a cosmic secret wrapped in darkness. Its origin story reads like poetry written in the language of gravitational mathematics, beautiful in its implications but frustratingly incomplete in its details. Its purpose, if such a word can meaningfully apply to wandering masses of rock or ice or something else entirely, stays locked in silence between the worlds. The object's very existence challenges assumptions about how thoroughly humanity has catalogued the solar system's contents. After decades of increasingly sophisticated sky surveys, after mapping the orbits of hundreds of thousands of asteroids and comets, after tracking objects from the innermost regions near Mercury to the distant Kuiper belt beyond Neptune, this substantial body remained hidden in plain sight. Its presence suggests that space still holds surprises for those patient enough to look carefully at the darkness between familiar lights. Like a gentle meditation on the nature of hidden things, the shadow object continues its slow dance around the Sun. It asks nothing of the planets it occasionally approaches in its orbital wanderings. It demands no attention from the star that provides the gravitational anchor for its endless journey. It simply exists in the cosmic quiet, carrying secrets that may be older than Earth's first oceans or stranger than anything born within this particular stellar neighborhood during the past 4.5 billion years of solar system history. The shadow object reveals itself most clearly not through what it shows, but through what it hides. Against the backdrop of distant stars, it moves like a piece of night that has learned to wander. Astronomers tracking its path watch as pinpoints of stellar light disappear behind its bulk, wink out for precise intervals, then reappear unchanged on the other side. These stellar occultations provide the most reliable method for studying something that refuses to reflect the sun's light back toward Earth's instruments. Each occultation event unfolds with the precision of celestial clockwork. The object approaches a background star along its predicted trajectory. The star's light beginning to dim at the edges where the shadow's gravitational field bends distant photons around its mass. Then, darkness arrives with mathematical certainty. The star vanishes completely for seconds or minutes, depending on the object's apparent size and relative velocity. Finally, light returns as the occultation ends, the star resuming its steady shine as if nothing had passed between it and Earth's telescopes. These disappearing acts occur with surprising frequency as the object moves through regions of space rich with background stars. The constellation fields behind Mars provide an abundance of stellar reference points, each one a potential probe for measuring the shadow's dimensions and trajectory. Only took billions of years for this cosmic hide-and-seek game to attract human attention. But now that observers know where to look, the object's presence becomes undeniable through its systematic erasure of distant light sources. The precision of these measurements reveals details that direct observation cannot provide. The shadow's edges appear remarkably smooth and regular, suggesting either a naturally rounded shape or a surface worn smooth by eons of micrometeorite bombardment and solar wind erosion. The occultation timings indicate an object roughly spherical in overall geometry, though subtle variations in different stellar encounters hint at possible surface irregularities, too small for telescopes to resolve directly. What puzzles astronomers most deeply is the object's apparent ability to absorb light across virtually the entire electromagnetic spectrum. Visible light vanishes completely during occultations, as expected. But radio waves, infrared radiation, and even some portions of the ultraviolet spectrum also show significant absorption or scattering when they encounter the object's bulk. This broad-spectrum darkness suggests a surface, material, or structure unlike anything else documented in the solar system's extensive catalogue of rocky and icy bodies. Most asteroids and comets reflect between 5 and 20% of the light that strikes them. Depending on their composition and surface texture, even the darkest known objects, rich in carbon compounds that formed in the cold outer regions of the solar nebula, still bounce back a few percentage points of incident solar radiation. This shadow object appears to reflect less than 1% of the light reaching its surface, making it darker than charcoal, darker than fresh asphalt, darker than any natural material found on Earth. The mystery deepens when scientists attempt to understand how such extreme darkness might arise from natural processes. Theoretical models suggest that certain configurations of organic compounds, perhaps similar to the complex carbon molecules found in interstellar space, could absorb light very efficiently across multiple wavelengths. Alternatively, the surface might consist of a highly porous material that traps photons in microscopic cavities, preventing their escape back toward space through multiple internal reflections and absorptions. Temperature measurements provide another layer of puzzlement for researchers studying the object's thermal behavior. Despite absorbing what should be substantial amounts of solar energy during its orbital journey, the shadow maintains a surface temperature only slightly above the cosmic background radiation that permeates all of space. This suggests either that absorbed energy somehow disappears into the object's interior without heating the surface, or that some unknown mechanism efficiently radiates heat away in wavelengths that Earth's instruments cannot detect. The object's thermal properties resist easy explanation within conventional models of planetary physics. If it absorbs solar energy as efficiently as observations suggest, its surface should glow brightly in infrared wavelengths, like a dark rock heated in sunlight. Instead, it remains almost invisible even to the most sensitive thermal imaging systems, as if the absorbed energy vanishes into some internal reservoir that never reaches equilibrium with its surroundings. This thermal behavior raises profound questions about the object's internal structure and composition. Perhaps it consists of materials with extraordinary thermal conductivity, spreading absorbed heat throughout its bulk so efficiently that no single surface region becomes noticeably warm. Perhaps it contains vast internal cavities that store thermal energy in convective circulation patterns, like a planetary-scale thermos bottle. Perhaps its darkness serves some active function in energy management that goes beyond simple absorption and radiation. Advanced computer models attempting to simulate the object's light absorption properties struggle to reproduce the observed effects using known materials and structures. The closest analogies in terrestrial physics involve artificially engineered metamaterials designed to trap specific wavelengths of electromagnetic radiation for technological applications. But such materials require precise manufacturing at microscopic scales, and their effects typically work only within narrow frequency ranges, unlike the shadow object's broad-spectrum darkness. The implications of such extreme light absorption extend beyond simple scientific curiosity. If natural processes can create materials this efficient at capturing electromagnetic energy, they might offer insights into fundamental physics that current theories have not yet explored. The object becomes a natural laboratory for studying interactions between matter and radiation under conditions that human technology cannot yet replicate in controlled environments. Meanwhile, the shadow continues its patient orbit through the space near Mars, occulting background stars with mechanical regularity. Each disappearance provides new data points for scientists attempting to map its shape, trajectory, and physical properties. Each reappearance of stellar light confirms the object's solidity and substantial mass. The darkness persists in its wandering, carrying mysteries that challenge conventional understanding of how matter behaves in the cold vacuum between worlds, like a cosmic meditation on the nature of absence and presence. The object defines itself through what it removes from view rather than what it reveals. It transforms the familiar brightness of distant stars into temporary voids, then returns them unchanged to the night sky. In this quiet dance between light and shadow, between visibility and concealment, the object maintains its secrets while offering tantalizing glimpses of properties that may revolutionize understanding of materials, energy, and the hidden complexities of planetary formation in the early solar system. The shadow object follows a path through space that tells a story written in the ancient language of gravitational mathematics. Its orbit carries the unmistakable signature of capture rather than native birth, the mathematical fingerprint of something that once wandered freely between stars before finding itself ensnared by our sun's patient gravitational embrace. Orbital mechanics specialists studying the object's trajectory recognize the telltale characteristics of what astronomers call a captured body, something that arrived from elsewhere and gradually settled into a stable dance around our local star. The orbital parameters reveal a history spanning millions of years, possibly tens of millions, during which the object's initial hyperbolic trajectory slowly transformed into the elliptical path it follows today. This transformation requires a complex series of gravitational interactions, likely involving multiple encounters with the solar system's giant planets during their own slow migration through the outer regions of space. Each close approach would have modified the object's velocity and direction slightly, the accumulated effects eventually binding it to our sun's gravitational domain. Jupiter and Saturn, those massive shepherds of the outer solar system, probably played crucial roles in the capture process. Their enormous gravitational fields extend far beyond their visible surfaces, creating zones of influence that can deflect, accelerate, or decelerate passing objects depending on the precise geometry of each encounter. The shadow object likely experienced several such gravitational assists over geological timescales, each interaction fine-tuning its trajectory until it achieved a stable orbit that could persist for billions of years without significant decay or ejection back into interstellar space. The mathematics of orbital capture reveal themselves in the object's current path, which carries it from the inner edge of the asteroid belt to regions just beyond Mars's orbit in an elongated ellipse that takes approximately 3 Earth years to complete. This orbital period places it in a complex gravitational resonance with several of the solar system's planets, a delicate balance that prevents close encounters with any major body while allowing the object to maintain its stable trajectory indefinitely. Only took the combined gravitational influence of multiple worlds to create such an intricate celestial choreography. What makes the orbit particularly intriguing is its slight inclination relative to the plane in which most solar system objects move. While the planets and most asteroids orbit the Sun in roughly the same flat disk that preserves the angular momentum of the original solar nebula, the shadow object's path tilts at an angle that speaks to its foreign origin. This orbital inclination suggests it approached our solar system from a direction perpendicular to the galactic plane, perhaps arriving during one of the Sun's periodic passages through the galaxy's spiral arms. The object's orbital eccentricity tells another part of its story, revealing the degree to which its path deviates from a perfect circle around the Sun. Highly eccentric orbits, stretched into long ellipses, typically indicate recent capture or ongoing gravitational perturbation. The shadow object's moderately eccentric orbit suggests it has had time to settle into a relatively stable configuration, but retains enough orbital energy to carry it through significant variations in distance from the Sun during each orbital cycle. At its closest approach to the Sun, called perihelion, the object receives substantially more solar radiation than at its most distant point, known as aphelion. This variation in solar heating should produce detectable changes in surface temperature and possibly even outgassing if the object contains volatile materials like water ice or carbon dioxide. Yet observations across multiple orbital cycles show remarkably little variation in the object's thermal signature, another puzzle in its growing catalog of mysterious behaviors. The gravitational perturbations caused by planetary encounters continue to influence the object's orbit in subtle ways that require decades of precise observations to detect and measure. Mars, during its own orbital journey around the Sun, occasionally approaches close enough to the shadow object to exert measurable gravitational influence. These encounters occur with clockwork regularity, allowing astronomers to predict future close approaches and plan detailed observational campaigns during periods of optimal viewing geometry. The long-term stability of the orbit depends on complex interactions between gravitational forces from all the solar system's major bodies, plus the subtle effects of solar radiation pressure and the gradual loss of orbital energy through gravitational wave emission. Computer simulations projecting the object's future trajectory suggest it will remain in its current orbital configuration for millions of years, barring unpredictable events like close encounters with other wandering objects or significant changes in the Sun's gravitational field as it ages and loses mass. These orbital characteristics provide crucial clues about the object's origin and composition. The trajectory analysis indicates it likely spent eons wandering through interstellar space before encountering our solar system, possibly originating in the debris disk around another star or forming in the cold outer regions of our own stellar neighborhood during the early stages of galactic evolution. The gravitational capture process suggests substantial mass, since smaller objects would have been more easily deflected back into interstellar space rather than trapped in stable solar orbits. The shadow object's arrival time remains uncertain, but evidence from its current orbital configuration suggests the capture process may have occurred during the late heavy bombardment, a period roughly 4 billion years ago when gravitational interactions in the outer solar system sent showers of asteroids and comets toward the inner planets. During this chaotic epoch, the gravitational architecture of the solar system was still settling into its current configuration, creating ideal conditions for capturing interstellar wanderers like the shadow object. Modern computer models of planetary migration during the solar system's youth predict that substantial objects could have been captured from interstellar space during this formative period, then forgotten in stable orbits until advanced telescopic surveys finally detected their presence. The shadow object may represent a remnant from this ancient era of cosmic turmoil, a messenger from the galaxy's deep past that has quietly maintained its orbit while Earth experienced the entire history of complex life, from the first photosynthetic bacteria to the development of technological civilization capable of detecting its presence. Like a patient clock marking cosmic time, the object continues its gravitational dance between the worlds, following laws of motion that Isaac Newton first described centuries ago, but which still govern the movement of matter through space on scales from falling apples to wandering planets. Its orbit preserves the memory of ancient encounters and gravitational negotiations that occurred before Earth's continents took their current shapes, before life colonized the land, before intelligence arose to contemplate the mathematics of celestial mechanics and wonder about the origins of dark objects drifting silently through the spaces between familiar worlds. The instruments trained on the shadow object speak in wavelengths of silence. Spectroscopy, that fundamental tool of astronomical investigation, struggles to extract meaningful information from something that absorbs rather than reflects the electromagnetic radiation necessary for compositional analysis. Where most celestial bodies reveal their chemical secrets through the characteristic fingerprints of absorbed and emitted light, this wandering darkness presents an almost featureless spectrum that challenges the basic assumptions of remote sensing techniques developed over centuries of astronomical observation. Traditional spectroscopic analysis relies on the interaction between matter and light to identify the elements and compounds present in distant objects. When sunlight strikes an asteroid's surface, specific wavelengths disappear from the reflected spectrum as atoms and molecules absorb photons at precise energies corresponding to their electronic and vibrational states. These absorption lines create a unique barcode that allows scientists to determine composition, temperature, and even surface texture from millions of kilometers away. The shadow object renders this elegant technique nearly useless through its comprehensive light absorption across virtually all observable wavelengths. The most sensitive spectrometers available to ground-based and space-based observatories detect only the faintest hints of spectral features in the minimal light that does reflect from the object's surface. What little signal emerges from the darkness shows broad, shallow absorption features that resist precise identification. These subtle spectral signatures suggest the presence of complex organic compounds, possibly similar to the carbon-rich materials found in the most primitive meteorites that occasionally fall to Earth. But the data remains too weak for definitive chemical identification. Advanced adaptive optic systems, designed to compensate for atmospheric turbulence and extract maximum detail from ground-based observations, push their technological limits, attempting to gather usable spectroscopic data from the shadow object. Even with these sophisticated correction systems, the object's extreme darkness reduces signal-to-noise ratios to levels that approach the fundamental limits of photon statistics. Only took 4 billion years of stellar evolution to produce instruments sensitive enough to detect this particular form of cosmic camouflage. Yet even the most advanced technology struggles to penetrate its secrets. The infrared portion of the electromagnetic spectrum, typically rich with thermal emission lines that reveal surface composition and temperature, shows equally puzzling characteristics when directed toward the shadow object. Most objects in space emit thermal radiation according to well-established physical laws relating temperature to wavelength and intensity. The shadow object emits far less thermal radiation than its absorbed solar energy should produce, suggesting either exotic thermal properties or internal processes that efficiently redistribute energy in ways that conventional models cannot predict. Polarimetry. The study of light's polarization properties provides another avenue for investigating the object's surface characteristics. When light reflects from most surfaces, it becomes partially polarized in patterns that reveal information about surface texture, composition, and grain size. The minimal light reflecting from the shadow object shows unusual polarization signatures that hint at surface structures operating on microscopic scales, possibly involving aligned particles or crystalline materials with specific orientational properties. Radio astronomy techniques, which can penetrate dust clouds and reveal hidden structures throughout the galaxy, encounter similar frustrations when focused on the shadow object. Radio waves that should reflect from solid surfaces or generate characteristic emissions from excited atoms and molecules disappear into the object's bulk without producing detectable echoes or emission lines. This radio silence extends across frequencies from long wavelength observations used to map interstellar hydrogen to short wavelength studies that probe molecular compositions in cometary comas and planetary atmospheres. The object's spectroscopic silence becomes even more mysterious when compared to other dark objects in the solar system. Carbonaceous asteroids, among the darkest naturally occurring bodies known to astronomy, still produce identifiable spectral signatures from clay minerals, organic compounds, and hydrated silicates formed during the solar system's early history. Even the enigmatic object Oumuamua, which puzzled scientists with its unusual properties during its brief visit to the inner solar system, reflected enough light to allow basic spectroscopic analysis of its surface composition. Laboratory experiments attempting to reproduce the shadow object's spectral properties focus on materials that might achieve such comprehensive light absorption through natural processes. Researchers have created artificial surfaces using carbon nanotubes arranged in forest-like structures that trap incident light through multiple internal reflections, achieving absorption efficiencies approaching those observed in the shadow object. However, these engineered materials require precise manufacturing techniques and would not survive the harsh radiation environment of interplanetary space for geological timescales. Theoretical models suggest that certain arrangements of organic polymers, possibly formed through radiation processing of simple carbon compounds over millions of years, could develop the complex molecular structures necessary for broad-spectrum light absorption. Interstellar space contains numerous organic molecules created through chemical reactions on dust-grained surfaces, and prolonged exposure to cosmic radiation could polymerize these compounds into materials with unusual optical properties. The shadow object might represent a natural experiment in organic chemistry conducted on planetary scales over cosmic timescales. Alternative explanations invoke more exotic possibilities, including surfaces composed of materials that interact with electromagnetic radiation through mechanisms not yet fully understood by terrestrial physics. Some theoretical frameworks predict that certain crystalline structures could channel absorbed photons into internal energy states that prevent their re-emission as thermal radiation, creating materials that function as perfect absorbers across multiple wavelengths. Such materials would exist at the boundaries of current scientific understanding, representing natural laboratories for investigating fundamental interactions between matter and energy. The spectroscopic mystery extends to the object's interaction with the solar wind, the stream of charged particles flowing constantly outward from the sun's corona. Most objects in space develop characteristic magnetic signatures and particle emission patterns when solar wind encounters their surfaces, creating detectable effects in magnetospheric instruments aboard various spacecraft. The shadow object appears to absorb solar wind particles as efficiently as it absorbs electromagnetic radiation, producing no detectable perturbations in the local space environment despite its substantial mass and cross-sectional area. Meanwhile, observatories around the world continue their patient accumulation of spectroscopic data, hoping that longer exposure times and improved signal processing techniques will eventually extract meaningful information from the object's electromagnetic whispers. Each observation adds photons to the growing database. Each measurement pushes instrumental sensitivity closer to theoretical limits. Each analysis explores new possibilities for understanding materials that challenge conventional classification schemes. Like a cosmic meditation on the limits of remote sensing, the shadow object maintains its spectroscopic silence while drifting through the space near Mars. It absorbs the questions posed by electromagnetic radiation without offering answers in the familiar language of reflected and emitted light. In this quiet resistance to analysis, the object embodies the fundamental mystery of matter itself. The question of how atoms and molecules arrange themselves into configurations that can drink starlight and transform solar energy into forms that remain hidden from even the most sophisticated instruments designed by human ingenuity to probe the secrets of distant worlds. The shadow object reveals its dimensions through the patient choreography of stellar disappearances. As it moves across the sky in its endless orbital dance, background stars vanish behind its bulk with precise timing that allows astronomers to map its shape through the careful measurement of occultation durations. Each stellar eclipse provides a cross-sectional glimpse of the object's profile, like examining a sculpture through its shadows cast on distant walls by lights positioned at various angles throughout space. The technique of stellar occultation represents one of astronomy's most elegant methods for measuring objects too distant or too dark for direct imaging. When the shadow object passes directly between Earth and a background star, the star's light disappears abruptly as the object's solid bulk blocks the photons that have traveled across interstellar distances to reach our telescopes. The duration of this eclipse depends on the object's diameter along the line of sight and its apparent velocity against the stellar background, providing geometric constraints that reveal physical dimensions with remarkable precision. Coordinated observations from multiple telescopes distributed across Earth's surface create a network of measurement points that map the object's shape through parallel occultation chords. Each telescope records slightly different eclipse timings as the object's shadow sweeps across the planet, creating a collection of parallel lines that trace the object's profile like the cross-sections used in topographic mapping. These measurements reveal an object roughly spherical in overall geometry, with a diameter of approximately 8 kilometers at its widest point. The spherical shape surprises researchers familiar with the irregular, potato-like forms of most asteroids and small solar system bodies. Objects this size typically lack sufficient gravitational self-attraction to pull themselves into rounded configurations, instead maintaining the jagged profiles created by collisional fragmentation and accretion processes. The shadow object's smooth, spherical outline suggests either formation under unusual conditions that promoted gravitational rounding or subsequent processing that eroded away surface irregularities over geological timescales. Only took millions of years of cosmic sandblasting to achieve such geometric perfection, assuming natural processes could account for its regular shape. Detailed analysis of occultation timing variations across different stellar encounters reveals subtle departures from perfect sphericity that hint at surface topography below the resolution limits of direct observation. Some occultations show slight irregularities in the eclipse curves, suggesting the presence of hills, valleys, or crater-like depressions that create minor variations in the object's silhouette when viewed from different angles. These features appear small compared to the object's overall diameter, indicating a remarkably smooth surface compared to typical asteroid terrain. The precision of stellar occultation measurements reaches extraordinary levels when multiple observers coordinate their timing to microsecond accuracy using atomic clocks and GPS synchronization. Professional and amateur astronomers participating in occultation networks can detect variations in eclipse duration corresponding to surface features just tens of meters in scale. This citizen science collaboration transforms the shadow object's passage into a distributed experiment spanning continents, with each observer contributing data points to the growing three-dimensional model of its shape and surface characteristics. Temperature variations across the object's surface, barely detectable in the most sensitive infrared observations, suggest that the spherical form may not be perfectly uniform in its thermal properties. Some regions appear slightly warmer than others, creating subtle temperature gradients that could indicate compositional variations, internal heat sources, or differences in surface texture that affect thermal radiation efficiency. These thermal patterns remain consistent across multiple orbital cycles, suggesting stable surface features rather than transient phenomena. The object's size places it in an interesting category between small asteroids and dwarf planets, large enough to be gravitationally significant but small enough to be strongly influenced by non-gravitational forces like solar radiation pressure and the solar wind. Its spherical shape becomes even more puzzling in this intermediate size range, where gravitational self-compression typically remains too weak to overcome the structural strength of rocky or icy materials. The smooth, rounded profile suggests formation mechanisms that remain poorly understood within current models of planetary accretion and evolution. Comparisons with other spherical objects in the solar system reveal the shadow object's uniqueness. Planets and large moons achieve spherical shapes through gravitational compression of their constituent materials, but they possess masses thousands of times larger than the shadow object. Some smaller bodies, like certain metallic asteroids believed to be the cause of disrupted planetesimals, show rounded profiles that result from their formation under high temperature, high pressure conditions during the early solar system's period of widespread melting and differentiation. The thermal properties associated with the object's spherical geometry raise additional questions about its internal structure and composition. A perfectly spherical distribution of mass would create uniform gravitational fields and predictable thermal behavior. Yet the object's temperature signatures show complex patterns that suggest internal heterogeneity. Perhaps the smooth exterior conceals a complex interior architecture of cavities, dense regions, or materials with varying thermal conductivities that create the observed temperature variations through internal heat transfer processes. Gravitational modeling based on the object's measured dimensions and inferred mass distribution suggests a bulk density comparable to common rocky materials found throughout the asteroid belt. However, this calculated density assumes uniform composition throughout the object's volume, an assumption that may not hold given the unusual surface properties and thermal behavior observed in other wavelengths. The object could contain substantial internal voids, dense metallic inclusions, or layered structures that would significantly alter its actual density distribution. The shadow object's size also influences its interaction with the solar system's various environmental factors. Objects of this diameter experience measurable effects from solar radiation pressure, which can slowly alter orbital trajectories over millions of years. The Yarkovsky effect, caused by thermal re-radiation from surfaces heated by sunlight, typically produces detectable orbital drift in objects this size. Yet preliminary orbital analyses show no clear evidence of such drift. suggesting either that the object's dark surface minimizes thermal re-radiation effects or that its internal thermal properties distribute absorbed solar energy in ways that cancel out the expected orbital perturbations. Advanced computer simulations attempt to model the object's formation and evolution using the size constraints derived from stellar occultation measurements. These models explore scenarios ranging from primordial accretion in the outer solar system to collisional formation through the merger of smaller bodies. Most formation mechanisms struggle to explain the combination of spherical shape, unusual surface properties, and stable orbital characteristics observed in the shadow object, suggesting that its origin story may involve processes not yet incorporated into standard models of solar system evolution. Like a cosmic exercise in geometric precision, the shadow object maintains its spherical perfection while drifting through the gravitational architecture of the inner solar system. Its smooth outline, revealed through the temporary eclipse of distant stars, speaks to formation processes that remain mysterious despite centuries of advancing astronomical knowledge. Each stellar occultation adds another data point to the growing understanding of its shape and size. Yet these measurements only deepen the fundamental questions about how such objects form and what materials could create such comprehensive darkness in the space between worlds. The gravitational whisper of the shadow object speaks in mathematics so subtle that only decades of precise planetary observations can detect its influence. Mars, that rust-colored wanderer in its predictable dance around the Sun, experiences tiny perturbations in its orbital path that reveal the presence of substantial hidden mass in its cosmic neighborhood. These gravitational signatures, measured in milliarc seconds of angular displacement and nanoseconds of timing variation, provide the most reliable evidence of the shadow object's physical reality and approximate mass. Planetary ephemerides. Those exquisitely precise tables that predict the positions of solar system bodies across centuries of time require constant refinement as observational accuracy improves and previously unknown influences become detectable. The motion of Mars has been tracked with increasing precision since the invention of the telescope, with modern radar ranging and spacecraft navigation providing positional measurements accurate to within a few meters across the vast distances of interplanetary space. Within this framework of extraordinary precision, the shadow object's gravitational influence appears as a systematic deviation from predicted orbital positions that accumulates over multiple Martian years. The detection of these gravitational perturbations requires sophisticated mathematical analysis that separates the shadow object's influence from the much larger effects of known planets, asteroids, and other solar system bodies. Jupiter and Saturn dominate the gravitational environment of the inner solar system, their massive presence creating perturbations in Martian orbital mechanics that dwarf the subtle influence of smaller objects. Advanced computer algorithms must account for these major influences, plus hundreds of smaller gravitational effects from asteroids, comets, and even relativistic corrections predicted by Einstein's general theory of relativity, before the shadow object's signature becomes visible in the data. The gravitational analysis suggests an object with mass comparable to a small asteroid, perhaps containing several billion tons of material compressed into its roughly spherical 8-kilometer diameter. This mass estimate, derived from the magnitude of orbital perturbations observed in Mars's motion, provides crucial constraints on the object's composition and internal structure. If composed primarily of rocky materials similar to common asteroids, the calculated density would fall within expected ranges for bodies formed through accretional processes in the early solar system. Only took 40 years of precision orbital tracking to accumulate sufficient data for detecting such subtle gravitational influences. The timing of gravitational perturbations correlates precisely with the shadow object's predicted positions along its orbit, providing strong evidence that this dark wanderer represents the source of Mars's orbital anomalies rather than some unrelated gravitational phenomenon. When the object reaches closest approach to Mars during its elliptical orbital cycle, the perturbations reach maximum strength. As it recedes to more distant portions of its orbit, the gravitational influence diminishes according to the inverse square law that governs all gravitational interactions in Newtonian mechanics. These gravitational measurements also reveal information about the object's internal mass distribution that cannot be obtained through other observational techniques. A perfectly uniform sphere would produce gravitational effects that depend only on total mass and distance, regardless of internal structure. The shadow object's gravitational signature shows subtle variations that suggest internal density variations, possibly indicating a differentiated interior with regions of varying composition or the presence of internal cavities that create mass concentrations in specific locations within the overall spherical form. The precision required to detect such weak gravitational signals pushes ground-based and space-based observational capabilities to their absolute limits. Radio tracking of spacecraft orbiting Mars provides some of the most sensitive measurements, as tiny changes in orbital velocity produce detectable Doppler shifts in radio communications between Earth and Martian orbiters. These spacecraft effectively serve as gravitational sensors, their precisely tracked trajectories revealing the presence of mass concentrations too small to detect through direct observation of planetary motion. Historical analysis of Mars, observations dating back centuries, reveals hints of the shadow object's gravitational influence in astronomical records that predate its visual discovery by decades. 19th century observations of Mars's position relative to background stars show systematic discrepancies with modern orbital calculations that exclude the shadow object's gravitational effects. These historical measurements, made with telescopes and timing techniques far less precise than modern instruments, nonetheless contain enough accuracy to detect the accumulated effects of gravitational perturbations over extended time periods. The gravitational data also constrains theories about the object's origin and evolutionary history. If the shadow object formed through conventional accretional processes in the asteroid belt, its gravitational properties should resemble those of other rocky bodies with similar mass and size. Alternative formation scenarios, such as capture from interstellar space or formation through unusual high-pressure processes, might produce internal structures that create distinctive gravitational signatures detectable through precision orbital analysis. Tidal effects, though extremely small at the distances involved, provide additional information about the object's gravitational field structure and internal mass distribution. Mars experiences minute tidal forces when the shadow object passes through closest approach during orbital encounters, creating barely measurable changes in the planet's shape and rotation that sophisticated geodetic techniques can detect. These tidal signatures complement the orbital perturbation data, providing independent confirmation of the object's mass and constraints on its internal structure. The long-term stability of the shadow object's orbit depends partly on its gravitational interactions with Mars and other planets, creating a complex dynamical system that evolves over millions of years through accumulated perturbations. Computer simulations projecting the orbital evolution forward in time must account for these mutual gravitational influences, plus the gradual effects of solar radiation pressure and other non-gravitational forces, to predict the object's future trajectory and assess the likelihood of eventual close encounters with major planets. Future gravitational studies may benefit from proposed space missions designed to measure gravitational fields with unprecedented precision. Dedicated gravity mapping spacecraft, similar to those used to study the internal structure of Earth's moon and other planetary bodies, could potentially detect additional gravitational anomalies in the Mars orbital region that might reveal the presence of other dark objects or provide more detailed information about the shadow object's internal architecture. The gravitational influence extends beyond simple orbital perturbations to include subtle effects on the rotation and orientation of Mars itself. The planet's spin axis experiences tiny precession effects caused by gravitational torques from nearby massive objects. And the shadow object's gravitational field contributes to these complex rotational dynamics in ways that precision measurements of Martian seasonal cycles and polar motion can potentially detect and quantify. Like a cosmic scale that weighs matter through its gravitational influence rather than direct measurement, the shadow object reveals its substantial mass through the mathematical language of orbital mechanics. Its gravitational whisper, barely detectable above the background noise of solar system dynamics, speaks to the fundamental interconnectedness of all matter in space, where even the most distant and invisible objects participate in the eternal gravitational conversation that shapes planetary motion and determines the long-term stability of orbital architectures spanning billions of years of cosmic evolution. The shadow object's origins may reach back to the solar system's earliest epoch, when planets condensed from swirling clouds of dust and gas in the primordial disk surrounding our young sun. During this chaotic period of accretion and bombardment, materials that would later form asteroids, comets, and planetary cores underwent complex processes of heating, melting, and chemical differentiation under conditions that no longer exist in the modern solar system. The object's unusual properties suggest formation during these extreme early conditions, possibly as a fragment of a larger body that experienced processing mechanisms capable of creating its distinctive dark surface and spherical geometry. Theoretical models of solar system formation describe a period roughly 4.5 billion years ago, when temperatures and pressures in the inner regions reached levels sufficient to melt rocky materials and drive chemical reactions that concentrated different elements into distinct compositional zones. During this era of widespread planetary differentiation, massive collisions between protoplanets created debris clouds containing fragments of partially melted and reprocessed materials. The shadow object could represent one such fragment, ejected from a collision event and subsequently modified by prolonged exposure to solar radiation and cosmic ray bombardment over geological timescales. The object's spherical shape provides crucial evidence for formation under high-temperature conditions that allowed gravitational forces to overcome structural resistance and create rounded geometries. Most small bodies in the solar system retain the irregular shapes imposed by collisional fragmentation and low-gravity accretion processes, lacking sufficient internal heat to achieve hydrostatic equilibrium. The shadow object's smooth outline suggests it experienced either formation in a molten or semi-molten state, or subsequent heating events that softened its constituent materials enough to allow gravitational rounding during a critical period of its early history. Chemical differentiation processes operating during the solar system's formation could explain the object's unusual light absorption properties through concentration of specific materials that naturally absorb electromagnetic radiation across broad wavelength ranges. Organic compounds synthesized under reducing atmospheric conditions, metallic glasses formed through rapid cooling of molten metal silicate mixtures, or complex carbon polymers created through radiation processing of primitive materials might all contribute to the comprehensive darkness observed in modern spectroscopic studies. Only took a few million years of high-energy processing to create materials with properties that continue to puzzle scientists billions of years later. The capture scenario that brought the object into its current orbit near Mars could have occurred during the late heavy bombardment, a period roughly 4 billion years ago when gravitational instabilities in the outer solar system sent showers of objects toward the inner planets. During this epoch, the migration of Jupiter and Saturn to their current orbital positions destabilized the asteroid belt and scattered debris throughout the solar system, creating ideal conditions for capturing previously unbound objects into stable solar orbits. The shadow object's orbital characteristics show signatures consistent with capture during this dynamically active period. Alternative formation theories suggest the object might represent a remnant of the original solar nebula that avoided incorporation into larger planetary bodies through some combination of orbital mechanics and compositional factors. Such primordial fragments would preserve materials and structures from the earliest stages of solar system evolution, potentially containing chemical and isotopic signatures that could reveal details about conditions in the pre-planetary disk. The object's resistance to spectroscopic analysis frustrates attempts to test this hypothesis directly, but future close-approach observations might detect trace signatures of primitive solar system materials. The thermal processing required to create the object's observed properties demands energy sources capable of heating substantial volumes of rocky or icy materials to temperatures sufficient for chemical reactions, phase transitions, and structural reorganization. Radioactive decay of short-lived isotopes present during the solar system's formation could provide such heating, particularly if the object formed with elevated concentrations of aluminum-26, iron-60, or other energetic isotopes that were abundant in the solar nebula but have since decayed to undetectable levels in modern samples. Impact heating represents another possible mechanism for creating the unusual materials and structures observed in the shadow object. High-velocity collisions between bodies in the early solar system generated enormous amounts of kinetic energy that converted to heat upon impact, creating temperatures and pressures capable of melting rock, vaporizing volatile compounds, and driving chemical reactions that produced novel materials not found under normal planetary surface conditions. The object could represent the solidified remains of such an impact event, preserving exotic materials created during moments of extreme energy release. Electromagnetic processing by the early sun's enhanced radiation output might also contribute to the object's distinctive properties. Young stars typically emit much higher levels of ultraviolet radiation and particle flux than mature stellar systems, creating harsh radiation environments capable of chemically modifying surface materials over extended exposure periods. Organic compounds subjected to such intense radiation could polymerize into complex structures with unusual optical properties, while rocky materials might undergo surface chemistry that creates light-absorbing mineral phases not commonly found in less irradiated environments. The timing of the object's formation relative to other solar system formation processes remains uncertain, but its orbital characteristics and physical properties suggest origins during the first few 100 million years of solar system history. This time frame encompasses the period of terrestrial planet formation, when Earth, Venus, and Mars were still undergoing major accretional events and experiencing the global heating episodes that created their differentiated internal structures. The shadow object might preserve a record of materials and processes from this formative epoch, serving as a natural museum specimen from the solar system's youth. Comparative studies with meteorites that have fallen to Earth provide the closest available analogs for understanding the shadow object's possible formation mechanisms. Certain classes of meteorites show evidence of high-temperature processing, rapid cooling, and chemical differentiation that created unusual mineralogies and structures similar to what might be expected in the shadow object's interior. However, no known meteorite type displays the comprehensive light absorption properties observed in the shadow object, suggesting either that it represents a previously unknown category of processed solar system material or that its surface has been modified by subsequent processes not recorded in the meteorite record. Computer simulations of early solar system dynamics attempt to model the formation and orbital evolution of objects like the shadow wanderer, exploring scenarios involving gravitational scattering, collisional disruption, and capture processes operating under the chaotic conditions that characterize the first billion years of planetary evolution. These models suggest that substantial numbers of processed fragments from the early bombardment period should remain in stable orbits throughout the solar system, many of them too small or too dark to detect with current observational capabilities. Like a messenger from the solar system's violent youth, the shadow object carries potential records of formation processes that operated under conditions radically different from the stable, predictable environment of the modern planetary system. Its dark surface may preserve chemical signatures of the high-energy events that shaped planetary cores, created the asteroid belt, and established the orbital architecture that has remained relatively stable for billions of years. In its patient orbit between Mars and the asteroid belt, the object maintains its secrets while offering tantalizing hints about the extreme processes that transformed a disk of gas and dust into the collection of worlds we observe today. The question of composition haunts every observation of the shadow object, its material nature remaining locked behind a surface that refuses to reveal its chemical secrets through conventional analytical techniques. Scientists studying the accumulated data find themselves confronting a puzzle that challenges fundamental assumptions about how matter behaves under the extreme conditions of space. The object's comprehensive light absorption suggests materials or structures unlike anything catalogued in terrestrial laboratories or meteorite collections. Yet it must consist of atoms and molecules governed by the same physical laws that apply throughout the known universe. Theoretical models exploring possible compositions focus on materials that could achieve such extraordinary light absorption efficiency through natural processes operating over geological timescales. Complex organic polymers, formed through radiation-induced polymerization of simple carbon compounds, represent one promising avenue of investigation. Interstellar space contains numerous organic molecules created through chemical reactions on dust-grained surfaces, and prolonged exposure to cosmic radiation could link these compounds into long-chain structures with unusual optical properties. The shadow object might represent a natural experiment in organic chemistry conducted on planetary scales over millions of years. Laboratory experiments attempting to replicate the object's spectral properties have produced artificially darkened materials using various combinations of carbon compounds, metallic particles, and porous structures designed to trap incident light through multiple internal reflections. Carbon nanotube forests, arranged in specific orientational patterns, can absorb over 99% of incident light across broad wavelength ranges. However, such structures require precise manufacturing techniques and would likely degrade under the harsh radiation environment of interplanetary space, making their natural formation questionable under realistic solar system conditions. Alternative theories invoke more exotic possibilities involving crystalline structures that interact with electromagnetic radiation through quantum mechanical processes not fully understood in current solid-state physics. Certain theoretical frameworks predict that specific arrangements of atoms in crystal lattices could create materials that absorb photons across multiple wavelengths and convert their energy into internal vibrational modes that never reach thermal equilibrium with the surrounding environment. Such materials would function as perfect absorbers while maintaining surface temperatures much lower than conventional thermal radiation laws would predict. The object's thermal behavior provides additional constraints on possible compositional models, ruling out materials that would glow brightly in infrared wavelengths when heated by absorbed solar radiation. Most conventional rock-forming minerals, even those rich in iron and other light-absorbing elements, would reach detectable thermal equilibrium temperatures when exposed to continuous solar heating during orbital passages through the inner solar system. The shadow object's minimal thermal signature suggests either exotic thermal conductivity properties or internal heat dissipation mechanisms that efficiently distribute absorbed energy throughout its bulk without creating localized hotspots detectable by infrared instruments. Metallic glass formations, created through rapid cooling of molten metal silicate mixtures under conditions that prevent crystalline organization, could potentially explain some of the object's unusual properties. Such materials combine the light absorption characteristics of metallic surfaces with the structural stability of silicate minerals, creating composites that might remain stable over geological timescales while exhibiting optical properties intermediate between pure metals and conventional rocky materials. The formation of substantial quantities of metallic glass would require specific cooling rates and chemical compositions that might have been achievable during certain high-energy events in the early solar system. Magnetic properties, though difficult to measure directly at such distances, could provide crucial clues about the object's internal composition and structure. Materials containing significant quantities of metallic iron or other ferromagnetic elements would create detectable magnetic field signatures when subjected to the solar wind's charged particle flux. The absence of obvious magnetic effects in the sparse data available suggests either low metallic content or internal structures that effectively shield magnetic materials from external electromagnetic influences through some unknown mechanism. Only took decades of increasingly sensitive magnetometric measurements to realize how little we understand about magnetic field generation in small solar system bodies. Density calculations based on the object's measured dimensions and gravitational effects suggest bulk properties consistent with rocky or metallic materials, but these estimates assume uniform composition throughout the object's volume. Internal cavities, layered structures, or significant variations in material density could substantially alter the relationship between overall mass and surface composition. The object might consist of a dense metallic core surrounded by layers of lighter materials, or conversely, a hollow structure with most of its mass concentrated near the surface in configurations that would create gravitational signatures similar to those observed in current data. Volatile content represents another compositional variable that could influence the object's observed properties and evolutionary history. Most objects formed in the outer regions of the early solar system contain substantial quantities of water ice, carbon dioxide, and other compounds that sublime when heated by solar radiation during orbital passages closer to the Sun. The shadow object's lack of observable outgassing or coma development suggests either formation in regions too warm for volatile retention or subsequent processing that removed or chemically bound volatile compounds into non-sublimating forms. Isotopic composition. Though impossible to measure directly with current observational capabilities, could provide definitive evidence for the object's origin and formation history. Materials formed in the solar nebula carry distinctive isotopic signatures that differ from interstellar matter, while objects originating around other stars would show isotopic ratios reflecting different stellar nucleosynthesis processes. Future close approach missions equipped with mass spectrometers capable of analyzing particles released from the object's surface through micrometeorite impacts or solar wind sputtering might eventually resolve questions about its stellar system of origin. Radiation processing effects could explain the transformation of initially conventional materials into the unusual substances now comprising the object's surface layers. Prolonged exposure to cosmic rays, solar wind particles, and ultraviolet radiation can chemically modify surface materials through processes that break molecular bonds, create new chemical species, and alter crystalline structures in ways that dramatically change optical and thermal properties. Such space weathering effects operate continuously on all objects in the solar system, but the shadow object's properties suggest either unusually intense radiation exposure or starting materials particularly susceptible to radiation-induced modifications. Comparative analysis with the darkest known objects in the solar system reveals the shadow object's uniqueness within the broader context of solar system materials science. Carbonaceous asteroids. Typically the darkest, naturally occurring bodies observable with current instruments, still reflect several percent of incident sunlight and show characteristic spectral features from clay minerals and organic compounds formed during aqueous alteration processes in the early solar system. The shadow object's near-perfect light absorption exceeds even these extremely dark materials by substantial margins, suggesting compositional or structural properties that remain without precedent in the known inventory of solar system objects. Future analytical techniques, including advanced neutron activation analysis and gamma-ray spectroscopy from close-approach spacecraft, may eventually penetrate the object's light-absorbing surface to reveal elemental compositions of subsurface materials less affected by radiation processing and surface modification. Such measurements could distinguish between competing compositional models and provide definitive evidence for exotic materials versus conventional substances arranged in unusual configurations that create the observed optical properties through structural rather than chemical mechanisms. Like a cosmic riddle wrapped in darkness, the shadow object guards its compositional secrets while drifting through the familiar territories of the inner solar system. Its material nature remains one of the fundamental unknowns in solar system science, a puzzle that challenges current understanding of how matter behaves under extreme conditions and raises questions about formation processes that may operate beyond the boundaries of conventional planetary science. Each new observation adds constraints to possible compositional models while deepening the mystery of what materials could create such comprehensive darkness in the space between worlds. The possibility that the shadow object originated beyond our solar system transforms its mystery from a local puzzle into a window onto the broader galactic environment and the processes that operate in interstellar space. If this dark wanderer indeed represents a visitor from another stellar system, it carries within its enigmatic bulk information about planetary formation processes, stellar evolution, and material science operating under conditions that may differ substantially from those that shaped our own cosmic neighborhood during the past 4.5 billion years of solar system history. Interstellar objects occasionally enter our solar system as they follow independent orbits around the galactic center, their trajectories occasionally intersecting the Sun's gravitational sphere of influence during the complex dance of stellar motion through the Milky Way's spiral arms. Most such visitors pass through the solar system on hyperbolic trajectories that carry them back into interstellar space after brief encounters with our local gravitational environment. The shadow object's current elliptical orbit suggests it underwent gravitational capture during such an encounter. Its initial hyperbolic trajectory gradually modified through planetary perturbations until it achieved stable orbital binding to our Sun. The capture process required precise orbital mechanics and fortunate timing that occurs relatively infrequently in astronomical terms. Computer simulations of interstellar object encounters suggest that successful capture demands specific combinations of approach velocity, trajectory angle, and gravitational assistance from the solar system's giant planets, Jupiter and Saturn. Those massive shepherds of the outer solar system likely played crucial roles in decelerating the object sufficiently to prevent its escape back into interstellar space. Only took several million years of orbital fine-tuning to achieve the stable configuration observed today. Stellar kinematic studies attempt to trace the object's trajectory backward through time to identify possible stellar systems of origin. The Sun's motion through the galaxy carries it past numerous other stars over millions of years, creating opportunities for gravitational encounters that could facilitate the exchange of planetary debris between stellar systems. Recent analysis of stellar positions and velocities measured by space-based astrometry missions reveals several candidate stars that passed within a few light-years of our solar system during time frames consistent with the shadow object's estimated capture date. The object's unusual material properties take on different significance when considered in the context of interstellar origins. Conditions around other stars, particularly during the violent epochs of planetary formation and early stellar evolution, could produce materials and structures not found in our solar system's inventory of naturally occurring substances. Different stellar compositions, alternative planetary formation scenarios, or exposure to radiation environments unlike those experienced by objects formed around our Sun might explain the shadow object's comprehensive light absorption and exotic thermal behavior. Interstellar space itself represents a harsh environment capable of modifying materials over the extended time frames required for travel between stellar systems. Cosmic ray bombardment, interaction with interstellar gas and dust, and exposure to radiation from multiple stellar sources could chemically and physically process object surfaces in ways that create novel optical properties. The shadow object's dark surface might record millions of years of such interstellar weathering, preserving evidence of material modification processes that operate only during extended journeys through the galaxy's vast empty spaces. The isotopic composition of materials formed around other stars would carry distinctive signatures reflecting the nuclear processes operating within their host stars and the chemical evolution of different regions within the galaxy. Elements heavier than hydrogen and helium are synthesized within stellar cores and distributed through space by supernova explosions, creating chemical gradients that vary with position in the galaxy and time since formation. An interstellar visitor would potentially carry isotopic ratios substantially different from solar system materials, providing definitive proof of its foreign origin if such measurements could be obtained through future close approach missions. Magnetic field interactions during interstellar travel could also contribute to the object's current properties and orbital characteristics. The galaxy's magnetic field, though extremely weak by terrestrial standards, extends throughout interstellar space and could influence the trajectories of electrically conductive objects during their million-year journeys between stars. Charged particle interactions with the object's surface might create or modify magnetic properties that affect its current behavior in the solar wind environment and its response to electromagnetic radiation across various wavelengths. The statistical probability of capturing interstellar objects depends on the density of such wanderers in the local galactic environment and the cross-sectional area of our solar system's gravitational capture zone. Recent estimates suggest that several interstellar objects of substantial size should pass through the solar system each decade, though most would remain undetected due to their high velocities and brief visibility windows. The shadow object's successful capture and long-term orbital stability represent a relatively rare outcome that preserves an interstellar visitor for detailed study over extended observational periods. Comparative studies with Oumuamua, the first confirmed interstellar object detected passing through our solar system, reveal both similarities and crucial differences that illuminate the diversity of materials and formation processes operating in different stellar environments. Oumuamua exhibited unusual acceleration patterns attributed to outgassing or radiation pressure effects, while the shadow object maintains a remarkably stable orbit with minimal perturbations. These differences suggest distinct compositional or structural properties that reflect the varied conditions under which interstellar objects form and evolve during their wandering journeys. The timing of the shadow object's arrival in our solar system, if indeed it represents an interstellar capture, coincides with periods of enhanced astronomical activity related to our Sun's passage through different regions of the galaxy, roughly every 30 million years. The solar system crosses the galactic plane where stellar densities and interstellar matter concentrations reach maximum values. During these crossings, encounters with interstellar objects, molecular clouds, and gravitational influences from nearby stars occur more frequently than during periods spent in the galaxy's less dense interstellar regions. Future detection and characterization of additional interstellar objects will provide statistical context for understanding the shadow object's properties and origin. Space-based survey telescopes designed to detect objects entering the solar system from interstellar space could identify incoming visitors years before their closest solar approaches, allowing detailed observational campaigns and potentially even intercept missions to sample their materials directly. Such studies would revolutionize understanding of planetary formation processes operating around other stars and the chemical evolution of materials in different galactic environments. The possibility of biological contamination, though extremely remote given the harsh conditions of interstellar space and the object's apparent lack of volatile materials, adds another dimension to questions about its origin and significance. If life exists around other stars and produces spores or other biological materials capable of surviving interstellar journeys, objects like the Shadow Wanderer could theoretically serve as vectors for biological exchange between stellar systems. Current observational capabilities cannot detect or rule out such possibilities, but future close-approach studies might search for organic compounds or other biosignatures preserved within the object's interior, like a cosmic time capsule from distant stellar neighborhoods. The shadow object potentially carries records of planetary formation, stellar evolution, and material science operating under conditions that may have no parallels within our local solar system. Its dark surface and mysterious properties could preserve evidence of processes that operate around different types of stars, in regions of the galaxy with alternative chemical compositions, or during epochs of galactic evolution when conditions throughout the Milky Way differed substantially from those prevailing today. In its patient orbit near Mars, this possible interstellar messenger maintains its secrets while offering hints about the broader galactic community of planetary systems and the materials they produce during their billions of years of evolution around distant suns. The temperature mystery surrounding the shadow object deepens with each infrared observation, revealing thermal properties that challenge conventional understanding of how matter exchanges energy with its environment in the vacuum of space. Despite absorbing what should be substantial amounts of solar radiation during its orbital journey, the object maintains a surface temperature barely above the cosmic background radiation that permeates all of space. This thermal behavior suggests either exotic heat dissipation mechanisms operating within its bulk, or materials science phenomena that efficiently prevent absorbed solar energy from reaching thermal equilibrium with the surrounding vacuum. Thermal infrared observations conducted across multiple orbital cycles reveal remarkably stable temperature readings that show minimal variation despite the object's changing distance from the Sun during its elliptical orbit. Most objects in space exhibit predictable temperature changes as they move closer to or farther from solar heating, with surface temperatures rising and falling according to well-established physical laws relating solar flux to thermal radiation. The shadow object's thermal stability suggests internal processes that buffer temperature changes or materials with extraordinary thermal conductivity properties that distribute absorbed heat so efficiently throughout its bulk that no localized warming occurs. The mathematical relationship between absorbed solar energy and expected surface temperature allows astronomers to calculate what the object's thermal signature should be if it behaved like conventional rocky or metallic materials. These calculations predict surface temperatures several hundred degrees above what infrared instruments actually detect, creating a substantial energy deficit that must be explained through unknown thermal processes or exotic material properties. The missing thermal energy represents a significant puzzle in the object's growing catalog of anomalous behaviors that resist explanation through standard models of planetary physics. Advanced thermal modeling attempts to explain the temperature anomaly through various heat transfer mechanisms that might operate within the object's interior structure. If the object contains extensive internal cavities or porous networks, absorbed solar energy could drive convective circulation patterns that efficiently transport heat from surface regions to interior zones where it radiates away through mechanisms not detectable by external infrared observations. Such internal thermal architecture would function like a planetary-scale heat exchanger, maintaining surface temperatures well below expected values while dissipating absorbed energy through hidden pathways. Alternative explanations invoke phase change materials that could absorb substantial amounts of thermal energy without corresponding temperature increases through processes like melting, sublimation, or crystalline structure transitions. If the object's composition includes materials with high latent heat capacities, absorbed solar energy could drive continuous phase changes that maintain constant surface temperatures while consuming thermal energy in molecular-scale structural rearrangements. Only took millions of years of solar heating to reveal how little we understand about thermal behavior in materials subjected to prolonged space weathering and radiation processing. The object's thermal properties also influence its interaction with the solar wind, that continuous stream of charged particles flowing outward from the sun's corona. Most objects in space develop characteristic temperature gradients when solar wind particles impact their surfaces, creating localized heating effects detectable through high-resolution thermal imaging. The shadow object shows no such thermal signatures, suggesting either that its surface efficiently conducts heat away from impact zones or that it somehow shields itself from solar wind interactions through mechanisms not observed in other solar system bodies. Laboratory experiments designed to replicate the object's thermal behavior focus on materials that might achieve such unusual heat dissipation properties through engineered microstructures or exotic material compositions. Certain metamaterials designed for thermal management applications can conduct heat with extraordinary efficiency while maintaining minimal temperature gradients across their surfaces. However, such materials typically require precise manufacturing techniques and would not naturally occur under the chaotic conditions of planetary formation or subsequent space weathering processes. Quantum mechanical effects operating at the molecular scale might contribute to the object's anomalous thermal behavior through processes that channel absorbed electromagnetic energy into internal vibrational modes that never reach thermal equilibrium with the surrounding material structure. Theoretical physics predicts that certain crystalline arrangements could trap photons in quantum states that prevent their conversion to conventional thermal energy, creating materials that absorb light without corresponding temperature increases. Such quantum thermal regulation would represent a natural phenomenon currently beyond the reach of human technology. The timing of thermal measurements across different orbital positions provides additional constraints on possible explanations for the temperature anomaly. If internal thermal processes create the observed temperature stability, these mechanisms must operate continuously regardless of the object's distance from the sun or exposure to varying levels of cosmic radiation. The consistency of thermal readings across multiple observational campaigns suggests stable internal architecture rather than transient phenomena that might vary with changing environmental conditions. Comparative analysis with other thermally anomalous objects in the solar system reveals the shadow object's uniqueness within the broader context of planetary thermal behavior. Certain comets exhibit complex thermal properties related to sublimation processes and internal heat transport through porous structures, but these effects typically create observable outgassing and coma development that the shadow object does not display. Some metallic asteroids show thermal inertia effects that delay temperature responses to changing solar illumination, but not to the extreme degree observed in the shadow wanderer. Future thermal studies may benefit from proposed infrared interferometry techniques that could map temperature variations across the object's surface with unprecedented spatial resolution. Such measurements might reveal thermal patterns, hotspots, or temperature gradients that provide clues about internal heat sources, structural features, or compositional variations not detectable through current single telescope observations. Advanced thermal modeling could then use these temperature maps to constrain theories about the object's internal architecture and heat dissipation mechanisms. The thermal mystery extends beyond simple temperature measurements to include questions about the object's thermal evolution over geological timescales. If it contains radioactive materials or other internal heat sources, these energy sources should gradually decay over millions of years, creating predictable changes in thermal output that careful long-term observations might eventually detect. The absence of obvious thermal evolution in available data suggests either very long-lived heat sources or thermal regulation mechanisms that maintain stable temperatures regardless of internal energy production rates. Magnetic field interactions could also influence the object's thermal behavior through processes that couple electromagnetic energy to internal material structures in ways that conventional thermal models do not consider. If the object contains materials with unusual magnetic properties, interactions with the solar magnetic field and interplanetary magnetic structures might create electromagnetic heating or cooling effects that contribute to its overall thermal balance. Such magnetothermal coupling would represent a previously unrecognized mechanism for energy exchange in solar system environments. The search for thermal analogies in terrestrial systems focuses on natural and artificial materials that exhibit similarly stable temperature characteristics under varying heat inputs. Geothermal systems, which maintain relatively constant temperatures through internal heat sources and efficient heat dissipation pathways, provide some conceptual parallels but operate on entirely different scales and under conditions unavailable in the vacuum of space. Understanding the shadow object's thermal regulation might require new theoretical frameworks that bridge planetary science, materials, physics, and quantum thermal dynamics. Like a cosmic demonstration of advanced thermal engineering, the shadow object maintains its enigmatic temperature stability while absorbing solar energy that should create substantial heating effects according to all conventional models of thermal behavior in space. Its thermal properties suggest internal processes or material characteristics that represent natural examples of phenomena currently beyond human technological capabilities, offering potential insights into thermal management techniques that might revolutionize understanding of heat transfer, energy storage, and temperature regulation in extreme environments, both terrestrial and extraterrestrial. The search for cosmic analogies leads astronomers through the catalog of the darkest known objects in space, seeking materials and surfaces that might provide clues to understanding the shadow object's extraordinary light absorption properties. Across the solar system and beyond, nature has produced various substances that absorb substantial portions of incident electromagnetic radiation, yet none approach the comprehensive darkness exhibited by this enigmatic wanderer. The comparison reveals just how unusual the shadow object truly is within the broader context of materials, science operating under the extreme conditions of space. Carbonaceous asteroids, those primitive remnants from the outer regions of the early solar nebula, represent some of the darkest naturally occurring bodies accessible to detailed study. These objects, rich in organic compounds and hydrated minerals formed during low-temperature chemical processes, typically reflect only 5 to 10% of incident sunlight. Their surfaces contain complex mixtures of carbon-bearing compounds, clay minerals, and other materials that form through aqueous alteration processes operating within asteroid parent bodies during the first few million years after solar system formation. Yet, even these extremely dark objects appear bright compared to the shadow wanderer's near-perfect light absorption. The asteroid Bennu, target of NASA's OSIRIS-REx sample return mission exemplifies the optical properties of carbonaceous bodies that formed in the cold outer regions of the solar system. Detailed spectroscopic analysis reveals surface materials dominated by phyllosilicate minerals and organic compounds that absorb substantial portions of visible and near-infrared radiation while still reflecting enough light to allow compositional analysis. The contrast with the shadow object's spectroscopic silence highlights the unprecedented nature of its light absorption efficiency and the challenges it presents to conventional remote sensing techniques. Comet nuclei provide another category of dark objects for comparison. Though their optical properties change dramatically as they approach the Sun and develop the bright comas and tails that make them visible to ground-based observers. The underlying solid nucleus of a typical comet reflects only 3 to 5% of incident sunlight, similar to carbonaceous asteroids but still far brighter than the shadow object. The seasonal variation in comet brightness as they approach and recede from the Sun also contrasts with the shadow object's remarkably stable optical properties throughout its orbital cycle. The mysterious object Oumuamua, that elongated visitor from interstellar space that passed through our solar system in 2017, exhibited optical properties somewhere between typical asteroids and the extreme darkness of the shadow object. Spectroscopic observations revealed a reddish surface composition possibly similar to organic-rich materials found in the outer solar system, but Oumuamua still reflected enough light to allow basic compositional analysis during its brief passage through the inner solar system. The comparison suggests that even interstellar objects, subjected to millions of years of radiation processing during their journeys between stars, do not typically develop the comprehensive light absorption observed in the shadow wanderer. Planetary ring systems contain countless small particles that collectively create some of the darkest, large-scale structures in the solar system. Yet individual ring particles retain detectable optical properties that allow detailed analysis of their composition and structure. Saturn's rings, composed primarily of water ice with various contaminants and organic compounds, reflect substantial amounts of sunlight despite containing regions of relatively dark material. Even the darkest ring features remain orders of magnitude brighter than the shadow object, emphasizing its unique position in the spectrum of solar system optical properties. Laboratory studies of the darkest known terrestrial materials provide additional context for understanding the shadow object's extreme optical characteristics. Freshly burned charcoal absorbs roughly 90% of incident visible light, while specially engineered carbon nanotube arrays can achieve absorption efficiencies exceeding 99% across specific wavelength ranges. These artificial super black materials require precise manufacturing techniques and carefully controlled microstructures that trap light through multiple internal reflections, preventing photons from escaping back toward external observers. The shadow object's natural achievement of similar or superior light absorption suggests formation processes or evolutionary mechanisms currently beyond human technological capabilities. Vantablack and other commercially produced ultra-dark coatings represent the current state of human technology in creating light-absorbing surfaces for specialized applications. These materials consist of carbon nanotube forests or other engineered structures designed to minimize reflection across broad wavelength ranges, achieving absorption efficiencies that approach theoretical limits imposed by fundamental physics. However, such materials remain fragile under normal environmental conditions and would not survive the radiation environment and physical stresses of interplanetary space over geological timescales, making their natural occurrence questionable under realistic solar system conditions. The comparison extends beyond simple reflectance measurements to include thermal properties that distinguish the shadow object from other dark materials in space. Most highly absorbing surfaces reach thermal equilibrium temperatures determined by the balance between absorbed solar energy and thermal radiation according to well-established physical laws. The shadow object's minimal thermal signature suggests either exotic heat dissipation mechanisms or material properties that prevent absorbed electromagnetic energy from converting to conventional thermal energy, creating optical behavior unprecedented in both natural and artificial materials studied under controlled laboratory conditions. Interstellar dust clouds represent some of the most extensive light-absorbing structures in the galaxy, containing microscopic particles that collectively obscure starlight across vast regions of space. These dust grains, composed primarily of silicate minerals and organic compounds formed around dying stars, absorb and scatter electromagnetic radiation through processes that create the dark nebulae visible in astronomical photographs. However, individual dust particles typically absorb only specific wavelength ranges and scatter substantial amounts of incident radiation, contrasting with the shadow object's comprehensive absorption across the entire observable electromagnetic spectrum. Only took billions of years of stellar evolution to create such extensive dark matter, yet individual grains remain far less absorbing than the shadow wanderer. Black holes represent the ultimate light-absorbing objects in the universe, capturing electromagnetic radiation so completely that nothing can escape their gravitational influence once it crosses the event horizon. However, black holes achieve their perfect light absorption through gravitational rather than material mechanisms, and their extreme gravitational fields create observable effects like gravitational lensing and accretion disk radiation that distinguish them clearly from material objects like the shadow wanderer. The comparison highlights the shadow object's achievement of near-perfect light absorption through purely material processes operating under normal gravitational conditions. Future comparative studies may discover additional ultra-dark objects within our solar system or in other stellar systems, providing statistical context for understanding whether the shadow object represents a unique anomaly or part of a previously unrecognized class of highly processed cosmic materials. Advanced sky surveys designed to detect extremely low reflectance objects could potentially identify similar dark wanderers that have escaped detection due to their minimal optical signatures, revolutionizing understanding of the true inventory of dark matter in planetary systems throughout the galaxy. The search for analogies also extends to theoretical materials predicted by advanced physics, but not yet observed in nature or created in terrestrial laboratories. Certain crystalline structures, exotic states of matter, or quantum mechanical phenomena could theoretically create materials with optical properties similar to those observed in the shadow object. Such theoretical frameworks provide conceptual foundations for understanding how natural processes might create materials that surpass current technological achievements in light absorption while remaining stable under the harsh conditions of interplanetary space over geological timescales. Like a cosmic benchmark for darkness itself, the shadow object establishes new extremes in the optical properties achievable through natural materials, science processes operating in space environments. Its comprehensive light absorption surpasses all known natural and artificial materials, suggesting formation or evolutionary mechanisms that remain beyond current scientific understanding. The comparison with other dark objects throughout the solar system and galaxy emphasizes its unique position in the spectrum of cosmic materials, challenging theories about the limits of light-matter interactions and inspiring new research into the fundamental physics of electromagnetic absorption in exotic material configurations. The quest to discern surface features on the shadow object pushes astronomical imaging technology to its absolute limits. As telescopes strain to extract structural details from something that absorbs virtually all incident light across the electromagnetic spectrum, high-resolution imaging campaigns coordinated across multiple observatories attempt to map topographical variations, crater patterns, and other geological features that might reveal clues about the object's formation history and evolutionary processes. Yet, the comprehensive darkness that makes the object so mysterious also renders it nearly invisible to conventional surface mapping techniques that rely on reflected sunlight to illuminate planetary terrain. Advanced adaptive optics systems, originally developed to compensate for atmospheric turbulence in ground-based astronomical observations, find themselves repurposed for the unprecedented challenge of imaging a surface that reflects less than 1% of incident radiation. These sophisticated systems use deformable mirrors and real-time atmospheric correction algorithms to achieve the theoretical resolution limits imposed by telescope aperture sizes. Yet even with these technological enhancements, the shadow object appears as little more than a smooth, featureless silhouette against the stellar background. Only took decades of adaptive optics development to realize how dependent surface imaging remains on adequate reflected light levels. Space-based telescopes, free from atmospheric interference and capable of extended exposure times, provide the most promising platforms for detecting subtle surface variations through accumulation of photons over extended observational periods. The Hubble Space Telescope and other orbital observatories can integrate light for hours or days, building up faint signals that might reveal topographical features invisible to ground-based instruments limited by atmospheric conditions and shorter exposure durations. Yet even these space-based observations struggle to extract meaningful surface detail from the minimal light reflected by the object's mysterious surface materials. Alternative imaging techniques explore wavelengths beyond the visible spectrum, seeking surface features that might become apparent in infrared, ultraviolet, or other electromagnetic bands where the object's absorption properties could differ from its comprehensive darkness in visible light. Thermal infrared observations attempt to map temperature variations across the surface that could indicate topographical features like ridges, valleys, or crater rims that create differential heating patterns when exposed to solar radiation. However, the object's remarkably uniform temperature distribution shows minimal spatial variation, suggesting either an extremely smooth surface or internal thermal regulation mechanisms that eliminate temperature gradients associated with topographical relief. Radar astronomy represents one of the most promising approaches for mapping surface features independent of optical reflectance properties, using radio waves transmitted from Earth-based installations and reflected from the object's surface to create topographical maps similar to those used for studying cloud-covered planets like Venus. The technique can penetrate surface materials to depths of several meters, potentially revealing subsurface structures and buried features not visible through optical methods. Unfortunately, the shadow object's radio silence extends to radar wavelengths, absorbing transmitted signals as efficiently as it absorbs visible light, making conventional radar mapping techniques ineffective. Stellar occultation observations, though limited to measuring the object's overall silhouette during passages in front of background stars, provide the highest resolution constraints available on surface topography through careful analysis of occultation timing variations. When surface features like mountains or craters alter the smooth outline of the object's shadow, they create tiny timing irregularities in stellar disappearances that can be detected through precision photometry coordinated across multiple observing stations. These measurements suggest a remarkably smooth surface profile with topographical variation smaller than a few hundred meters, indicating either formation processes that produced naturally smooth surfaces or subsequent modification through erosion or other surface smoothing mechanisms. Computer modeling attempts to simulate possible surface structures that could remain hidden within the limitations imposed by current observational capabilities. Digital elevation models explore various crater densities, ridge patterns, and geological features that might exist on scales too small for direct detection while remaining consistent with occultation measurements and thermal observations. These theoretical surface maps serve as templates for planning future close approach missions that could provide definitive topographical data through high-resolution imaging, laser altimetry, and other proximity-based measurement techniques. The absence of observable surface features raises fundamental questions about the object's geological history and the processes that shaped its current appearance. Most solid bodies in the solar system bear extensive crater records from billions of years of impact bombardment, creating surface textures that preserve detailed histories of collisional evolution and modification. The shadow object's apparently smooth profile suggests either formation in an environment with minimal impact flux, composition dominated by materials that do not retain crater structures, or surface modification processes that continuously erase impact features through mechanisms not commonly observed in other solar system bodies. Micrometeorite bombardment, operating continuously throughout the solar system, typically creates surface textures and regolith layers that should be detectable through careful analysis of reflected light polarization and scattering properties. The shadow object's optical behavior shows minimal evidence of such surface weathering effects, suggesting either recent surface renewal through unknown processes or materials that do not develop conventional space weathering characteristics under prolonged exposure to interplanetary dust and radiation. The implications extend beyond simple surface mapping to fundamental questions about material stability and geological evolution in space environments. Gravitational field mapping, though challenging at the distances involved, could potentially reveal internal structure variations that influence surface topography through processes like tidal deformation, internal mass redistribution, or geological activity driven by radioactive heating. Subtle variations in the object's gravitational field during close approaches to Mars might indicate internal cavities, dense regions, or other structural features that could manifest as surface expressions detectable through future high-resolution observations. Such gravitational archaeology could reveal hidden complexities within the object's apparently smooth exterior. The search for surface features also encompasses spectroscopic variations that might indicate compositional differences across the object's surface, even within the constraints imposed by its comprehensive light absorption. Advanced spectroscopic techniques designed to detect minimal reflectance variations could potentially map regions with slightly different absorption properties, revealing compositional heterogeneity or geological processes that created spatial variations in surface materials. However, the extreme uniformity of the object's spectroscopic signature suggests remarkable compositional homogeneity or surface processing that has eliminated detectable chemical variations. Future surface mapping efforts may benefit from proposed artificial illumination techniques using powerful laser systems or coordinated spacecraft formations that could provide controlled lighting conditions for high-resolution topographical studies. Such active illumination experiments could potentially reveal surface details invisible under natural solar illumination, though the object's comprehensive light absorption properties suggest that even artificially enhanced illumination might prove insufficient for conventional surface mapping approaches requiring adequate reflected light levels. Close approach missions equipped with specialized imaging systems designed for ultra-low light conditions represent the most promising avenue for definitive surface characterization of the shadow object. Such spacecraft could carry sensors optimized for detecting minimal reflected signals, laser altimeters for direct topographical measurement, and other instruments capable of surface analysis independent of optical reflectance properties. The technical challenges of imaging an essentially black object in space would drive development of new sensor technologies, with applications extending far beyond this particular target. Like a cosmic meditation on the limits of remote observation, the shadow object maintains its topographical secrets while drifting through regions of space where countless other bodies reveal their surface histories, through the interplay of reflected sunlight and geological processes. Its smooth, featureless appearance in current observations may conceal complex surface structures awaiting discovery through future technological developments. Or it may genuinely represent a body whose formation and evolution produced surfaces unlike any others, catalogued in the extensive inventory of solar system geological diversity. The shadow object's gravitational influence extends beyond simple orbital perturbations to include subtle light-bending effects that challenge current understanding of its mass distribution and internal structure. When background starlight passes close to the object's gravitational field, the light undergoes minute deflections predicted by Einstein's general theory of relativity, creating gravitational lensing phenomena detectable through precision astrometry and photometry. These effects, though extraordinarily small at the modest gravitational field, strengths generated by objects of this size provide independent constraints on the shadow wanderer's mass and reveal hints about its internal architecture that remain hidden from conventional observational techniques. Gravitational lensing occurs when massive objects bend the fabric of space-time sufficiently to alter the paths of photons traveling past their gravitational influence zones. For stellar mass objects like black holes or neutron stars, such effects create dramatic distortions in background images that are easily observable with modern telescopes. The shadow object, with its relatively modest gravitational field, produces lensing effects measured in micro-arc seconds that push ground-based and space-based astrometric capabilities to their absolute precision limits. Only took a century after Einstein's theoretical predictions to develop instruments sensitive enough to detect gravitational lensing by small solar system bodies. The mathematical analysis of gravitational lensing effects requires sophisticated modeling that accounts for the object's gravitational field geometry, the precise positions of background light sources, and the observer's location relative to the lensing configuration. Computer algorithms designed for such calculations must consider relativistic corrections to Newtonian mechanics, plus the complex interplay between the object's gravitational influence and the Sun's much larger gravitational field that dominates the local space-time curvature throughout the solar system. The resulting lens equations produce predictions for light deflection angles and image magnifications that can be compared with observational measurements to constrain the object's mass distribution. Preliminary lensing observations, conducted during optimal alignment geometries, when the shadow object passes between Earth and bright background stars, reveal deflection signatures that suggest internal mass concentrations inconsistent with uniform density distributions. If the object consisted of homogeneous rocky or metallic materials, its gravitational lensing effects would follow predictable patterns determined solely by total mass and overall shape. The observed lensing signatures show subtle deviations from such uniform mass models, hinting at internal structures that create gravitational field variations on scales comparable to the object's overall dimensions. These gravitational anomalies could result from various internal architectural possibilities, including large cavities that reduce local gravitational field strengths, dense metallic cores surrounded by lighter materials, or complex layered structures that create gravitational field gradients not achievable through simple spherical mass distributions. The lensing data suggests gravitational field variations that would require internal density contrasts of at least 50% between different regions within the object's volume, implying either formation processes that naturally created such heterogeneous structures or subsequent geological evolution that redistributed mass through internal dynamical processes. The timing of gravitational lensing effects provides additional constraints on the object's internal structure through analysis of how light deflection varies as background stars move relative to different portions of the gravitational field. If the object contains rotating internal components, massive liquid cores, or other dynamically active internal structures. These would create time-variable gravitational signatures detectable through careful monitoring of lensing effects during extended observation campaigns. The apparent stability of observed lensing patterns suggests solid internal architecture rather than fluid or granular materials that might redistribute mass over observable timescales. Advanced astrometric techniques, developed for detecting exoplanets through gravitational wobbles in stellar positions, find new applications in measuring the shadow object's gravitational lensing signatures with unprecedented precision. Space-based observatories equipped with micro-arc-second astrometric capabilities can track background star positions with accuracy sufficient to detect gravitational deflections caused by objects much smaller than previously accessible to lensing studies. These measurements provide geometric constraints on gravitational field structure that complement traditional orbital perturbation analyses, while offering insights into mass distribution mechanisms not accessible through other observational approaches. The search for gravitational lensing effects also encompasses photometric variations in background star brightness that could result from gravitational focusing of starlight during close alignment events. When the shadow object's gravitational field acts